Okay, so this section's on exothermic and endothermic reactions. You've got two contrasting words here where we would say exo, exit, exterior, outside, gives energy out, usually in the form of heat. So exothermic reactions will feel hot, and the opposite of exothermic is endothermic. Endothermic have to take heat in from the surroundings. Endothermic reactions will feel cold. Make sure you've got that clear. Exothermic give out heat energy. If you were holding a test tube with an exothermic reaction going on, it would feel hot. Endothermic reactions take extra energy from the surroundings and cool the surroundings down. If you were holding a test tube with an endothermic reaction going on, it would feel cold. And these types of diagrams, which are called reaction profiles, are used to show the energy change, and you need to know a few specific things about them. So this arrow going upwards represents the amount of energy. We've got our reactants, whatever they are, at a certain point, and always energy has to be put in to break bonds, and the amount of energy required to break the bonds is referred to as the activation energy. So in this diagram, the activation energy is the amount of energy between the peak of that hill and the position where the reactants are. Okay, so the activation energy, how much energy this stuff here, ammonia and oxygen, have to get this much activation energy in order to react and become these products down here. So there's a total amount of energy which is going to be released to the surroundings, which is this, and then finally here the overall energy change is the difference between these two amounts. So between this point here and the energy position of the products is the overall energy change. And as you can see, in this case, you get out more energy than you had to put in. The energy change will be heat given out to the surroundings, and this is the reaction profile for an exothermic reaction. Okay, let's compare that to endothermic. So here I've got a reaction profile for an endothermic. Everything is the same. So you've got the reactants here, the amount of activation energy that is required to break apart bonds, the amount of energy that is given out as bonds are made, which is B, but notice the products here have more energy than the reactants over here, and in order to do that, this amount of energy has to be taken in from the surroundings. The overall energy change is C. Okay, and this is endothermic because the energy released when the products were formed is smaller than the activation energy at the start. Okay, in other words, the energy to break bonds is bigger than the energy from making bonds, and the difference has to be taken in from the surroundings. Okay, this is the reaction profile for an endothermic reaction. So just looking, going back again, you can see, think of exothermic reactions as going down the hill of energy and things becoming more stable. Whereas in an endothermic reaction, think of reactions ending up higher up the energy hill than they started from, and the products having extra energy stored inside them. Photosynthesis is an endothermic reaction. The energy from the sunlight that goes in is taken on board, and some of it is trapped in the glucose molecules that the plant's made. So photosynthesis is a biological chemical reaction that is endothermic, and you will know that respiration is the opposite of photosynthesis, and respiration is exothermic. When we do, or plants do, or any living creatures do respiration, we are releasing the energy stored in glucose so that our muscles can contract and we can keep warm and all of those things.